Hi, good evening, everyone. My name is Tatiana. You can call me Tati. Thank you so much, Matthias, for organizing. It is so good to see some real people and be able to have conversations face to face. So a bit about me. I'm Brazilian. I've been living in the UK for 7 years now. I work developing software for almost 20 years now. I love computers. And I love open source. And I started using Apache Beam in early 2019. And I would say I work for the BBC. Our team is called Data Lab. And I would say we're in very early stages in our data journey. So it is quite interesting to see what Peter and Mark presented. And I would say we're a bit behind, but hopefully at some point the BBC will reach that level of maturity. The work I will be presenting here, it's the work of many people. The people who got their hands dirty, so I could show some of these results are Darren Mundi, Richard Bounds, myself, and some team members who left. So it's Bettina, David, Gianna, and Mark. And David has attended most of the Apache Beam meetups in London, but unfortunately he couldn't be here. So all these people contributed to this. Our business context for this presentation. So the BBC had this third-party provider to provide recommendations for our apps, both iPlayer and BBC Sounds, and they wanted to replace it. And the idea was, could your team build that so we can replace, so the BBC can have the knowledge, improve it, and we can end the contract with the third-party provider. The numbers were much smaller than what Mark showed to us. So we were talking about 6.5 million of users for whom we would like to have personalized recommendations. And the content we were wanting to match those users with was around 200,000 podcasts and episodes. And out of that content, the idea was to select the 9 most relevant episodes or 12 most relevant episodes per user. So the problem would be basically, given all this amount of content, just to spot this bit, which would be more meaningful for the users. On top of the traditional recommendation engine, the BBC has a few business rules which we had to apply. So some examples. We should diversify the recommendations. So we don't want to have the audience bias towards something. So one of the properties we use for that is brand. Recency. In the case of content which is news, we want to make sure we're not giving outdated information. There's the narrative arc as well. Let's say you've been watching some drama series or something where it makes sense to have a sequence. You're in the middle. We shouldn't be recommending the episode just before that. And then language-wise, we shouldn't be recommending Gaelic content to users who didn't have a meaningful consumption of Gaelic content. The content must be available. Some of the content falls out of availability, and exclude some types of content which might not be very relevant to users, such as the shipping forecast, but some users love them and use them to sleep and so on. But I'm sorry, our recommendations won't have them, but you can still get them in our services. Yeah, so a bit about the technology. We remained with Python, so most of our team is made of data scientists, and we remained with Python throughout. I would say most of our challenges were not Python related until now. We use Google Cloud Platform, Airflow, Apache Beam. We've been using the data flow runner. And we use this technology, which many of you might not know, which is LightFM, which I also didn't know. And that was a decision from our data scientists. They said, this is an amazing factorization machine model. Let's use it. And by the time we were busy building lots of things, so we said, OK, let's just follow with that. Let's give up on TensorFlow and those things. Let's use this model that doesn't scale horizontally nor anything, just to give a try, since their analysis was, this model is good. A bit of the pipeline we build. So we have a few pipelines. Some of them relate to ingesting user activity. some of them to the content metadata. We process those things. We have to train the model using LightFM. We have some artifacts. We then predict. We have a set of predictions. On top of the predictions, we apply rules, and then we have the filtered predictions per user. So what we're talking about, the dimensions would be, as I said, around 6.5 million in one side against 200,000 items on the other. And that's where we used Apache Beam. So it's being used throughout our stack. We've been quite consistent on using Apache Beam. Some example of the data. This is how we represent an episode. Very simple metadata, some time related, some array, some strings or IDs. The user at the moment is just ID. The idea is to explore more features, and the user interactions are like that. The model we use would allow more. This was just the starting point. And this is an example of how the data would look like for each of those data structures. The output is basically the user ID and then a sequence of identifiers of episodes and the score we give for them, and it should be ordered. So the first step was, can we build that with the skills we had and with the technology we had? So we did some spike on pre-computing things with this LightFM model, and we just wrote some very quick and dirty Python script, run each a VM, and we saw, okay, from our estimates, if we want to pre-compute Rex for 6.5 million users, we might be able to achieve that for around $250 a month if we were to have a VM and we would spin up, tear down, and so on. So we thought, okay, the pre-compute recommendations for our scale will work fine. That's not the issue. Then we started playing with sorting some of the predictions if we were to use just pure Python, and that didn't quite scale as someone might expect. So we wanted to sort, let's say, 100K predictions per user, and it was extremely slow, inefficient. It was just the wrong tool for it. Perhaps we should have looked at Drage for them. So there was a bit of the concern if we weren't being able to just using plain Python to make it scale, who would say the other complex rules? So we thought, let's try to use Beam to parallelize that so we can try to improve the scale. So the initial scope, the first objective was we just need to get rid of that external provider, having a better result in the A/B test. So we thought, okay, let's do cuts to our data just so we can simplify the problem. So the first thing was, okay, do we really need to compute for 6.5 million users? Do we really need 200K items? Does each matter a whole year of the user activity? Do we need to run it 3 times a day? And do all rules need to be applied after pre-computing? So we just made cuts everywhere to simplify the problem. So we said, okay, let's just compute recommendations for users who have more than 3 items of activity. Because people who just consumed 1 item, it might be very biased, any recommendation we gave. Also, we noticed that we could apply some of the rules beforehand, other than having to apply after pre-computing regs. So that allowed us to cut to half. We also moved to only consider 4 months of user activity. And from 3 times a day, we said, let's just try to run this batch thing twice a week. That should be a good start. And I tried to add the dates there, and this might be relevant for the data flow aspects of it. So this is more or less how it worked. We then applied some of the rules before pre-computing. Then we would have to pre-compute against half the items, and then we would apply the rules after. So the problem got a bit simplified. And then the other thing was, why do we need to sort 100K items per user if we're only surfacing the end 9 to 12 items? So we just decided to calculate the 90 percentile and just keep the ones with the highest score, and then we would sort only that fraction per user. So this simplified a lot the processing we had to do per user, because we were just trying to sort 10K items or less, opposed to 100K items per user. So the pipeline evolution, and this was quite similar to what Mark described in the sense that it's useful to have a representative data since the beginning when you're designing the pipeline. So our initial idea was, okay, let's try to have the single beam pipeline, which would pre-compute recommendations and apply those rules. This is how it looked like for direct runner with some sample data. It was beautiful. And then when we tried to run with data flow with a bit more realistic volume of data, it miserably failed. So it was a complete disaster. We were trying to use the standard machine type. We noticed from other pipelines we built that by the time auto-scaling would usually cost us, I don't know, 20% more. So we tried to stick at that moment in time to have fixed amount of workers and disabling auto-scaling. This was August 2020. So the steps were, we would ingest the user activity from one side. We would ingest the program metadata from another side. There were two sources of program metadata. We would sort of merge the two things due to the way we process the rules. I will make this clearer after. We would then create predictions, and then we would apply rule by rule. So if anyone has any question, please do say. I know you must be hungry by now, but this, you can just ask questions. It might make better. So the problem when we try to run this, we would get this error from data flow saying the worker lost contact with the service, which was very funny. And when we got that, we would usually just check the VM, see more or less it's running out of memory, and then just collapsing. So we tried to just, let's give it a larger VM. And, but before, we analyzed the volumes of data. So by the time the model we were talking about was around 4.5 gigabytes in RAM, and we had to load the model in memory so we could infer the recommendations per user. There were some auxiliary data structures which we would also need to have loaded in memory in the process. Some were needed for rules, others for pre-compute. We were really doing just loading things in memory. And this would be more or less the amount of data we would have to have concurrently in memory for each executor or process or perhaps thread to some extent. And that's what we try to improve after. So the first attempt to fix the pipeline was just, okay, given our memory requirements, let's just get a machine where we could fit things. Initially, we tried the custom 16656. It was the highest ratio by default GCP allowed us to do. And then we just went, like it wasn't working, we just got this gigantic instance with 24 gigabytes of RAM per core, and that worked. But obviously, it was really like, I don't know, it was too much. We knew it was overkill, but we just really wanted to see the thing working. We refactored the pipeline. We tried to use reshuffle on some of the parts of the pipeline to distribute in better batches or something. We increased the amount of workers. We tried to get control of how Beam was working, data flow was processing things. So we tried to understand how the harness threads, SDK workers, the containers, play with lots of parameters by the time. And it was a complete disaster. We talked to our Google account manager. He said, no, you guys are doing something very wrong. And yes, we know it's not working. So we then shared our problem with the community. And we said, look, guys, we know we're wasting lots of resources. Does anyone have any idea there? And then just to make it more visible, we pinged the by the time data flow product manager in Google, Sergey, and luckily we got some feedback. So the ideas were, why don't you try using this just released feature, the shared memory, so you could have multiple threads within the same process, just loading once the model in memory, and then you could share that, and it will be more efficient. And the other help we received was, okay, why aren't you using this option X, which allows you to use a different ratio of memory allocated per core? And so this was certainly easier. So we just adopted this straight away. And then we said, OK, let's try shared just after. So we managed to achieve the goal. We implemented this first version of the pipeline. It looked very bad, but it did work. We were not using that gigantic machine with 24 gig of RAM per core. And it allowed us to get rid of the external provider of recommendations. So this is how much we managed to get and to increase with the user interactions. For the BBC, it was, again, from a data engineering perspective, it was a disaster. But from a BBC business perspective, we managed to deliver what they wanted. And the costs were very high. So we were using batch, we were not using streaming. This is the type of cost we were seeing per run of this pipeline, which was obviously shameful, right? So we knew we need to do something about this. And then while this pipeline was live, we also had an interesting issue of a pipeline running, I don't know, for 2-3 months. And then all of a sudden, it started complaining of no space left into disk. And we noticed that shuffle had been enabled without us doing anything. And it seems it was just a change in the data flow service where they changed the default behavior. And this was not documented in the release notes we saw. But then we just gave a different parameter to disable it because the pipeline didn't work well with shuffle by the time. So then we had to do lots of other things. And this pipeline was there, living its life, just running, spending tons of money. And then we had a plan. So our plan was, what is the minimal thing we can do to try to save costs? Because we don't like this pipeline. It's too expensive. We can make better. So we thought, let's try the shared memory thing. We could try FlexRS. So we would be using the preemptible instances. It is OK. We're just running this thing twice a week. Who will complain if it takes 8 hours to schedule? No one. The second option was, you know what? What if we just computed for the users who are using the app more? So we try to give those users more care and love, computing more often for them, and we leave some of the other millions users behind. And then what we thought had to be done, but we were a bit afraid, was the actual heart surgery, where we would just split the pipeline and say, OK, rules to one side, predictions to the other, the inference. We would refactor, and then we could even change how we were inferring things, replacing LightFM to scan. So we had a few plans. And the timelines, which obviously were not matched. So this was the design for the predict. Let me see. OK. So the first step was, let's just try to use shared memory, and let's just try to use FlexRS, and we see how much we get from that. No major changes to the pipeline. Those things should help to some extent. But there was a concern, because since the shared memory was shared memory across the threads of a single process, and there is the Python GIL, Global Interpreter Law, there was a concern of how much that would actually give of benefit, because the threads would potentially be competing to predict things. So we weren't sure, but we were hopeful. So the strategy we used was, we learned we needed to have some representative data. So to just use a smaller mod and things, those things didn't help us. But we thought, what if we keep the model, we keep all the other data sets we're having to load in memory, and we just run the pipeline for a fraction of the users. So it would be on the horizontal side, opposed to computing while we're optimizing and studying for the 3.5 million users. Why don't we just get less than 1% of the users? We try to optimize, we keep the model, all the other things there. And then we make that cheap, and then we will be able to get the same gain when we consider the 100% of the users. So the first strange thing was, to run for 100% of the users costed 266 pounds, this particular run. But to run for 0.5% of the users was 80 pounds. And when we saw that, oh, what are we doing wrong? There is something intrinsically wrong to the pipeline itself. This was using the exact same parameters. The same parameters, same VM, same model, everything. So, oh my goodness. But then we thought, well, we don't know much about this. Let's try to improve this. It is bad, but then the proportion when we go back should be the same, right? So the idea was the same way there was this ratio here. When we go back, hopefully this ratio will be applied and the savings will be there. So we implemented shared memory in loading the model in the predict step. And we started reducing the VM size, analyzing inside the VMs, monitoring with the memory consumption, how much threads we're using, etc. And we were able to reduce from 80 pounds to 18 pounds, so 77% of cost reduction for this fraction of users. And then we thought, well, that's something. It looks nice, because if we're able to reduce to 1/4 the cost, this will significantly decrease. We didn't have much effort. However, when we try to apply that for the 100%, the pipeline would take hours to run, and it wouldn't complete. And I know, this was very strange. So if anyone would like to discuss this later, we tried to do a very methodological approach where we really use the same data. We have Git commits mapping, which were the runs. We have the data flow IDs, what changed between each step. We committed every change. And we just run the iterations. We made some comments about how was the behavior and things. And I must confess, it was quite disappointing to see that just adopting shared memory with the pipeline we had didn't lead us anywhere. Our hypothesis is that we had designed the pipeline quite poorly, so in many aspects. But one of them was we represented the data in a very expensive way per user. So let's say a user had, I don't know, 1,000 recommendations, and the user had consumed 500 items. We didn't represent those things just as speeds, just the identifiers. We actually represented with the full program metadata associated to that item. So it wasn't much. We thought, you know what, that's not much. Why should it matter, right? So it was this amount of data for each of those items per user. But probably due to the way Beam parallelizes things inside and how it splits the works and things, I suppose that to process thousands of those things concurrently would load in memory and would have other impacts. And probably having to move those things from steps distributed across VMs was certainly suboptimal, because the program metadata was constant, right? So there had to be a better way of doing that. So after a few attempts, we said, OK, let's just go to the hard surgery. And so we got to the predict step, and we said, that's a problem of itself. It's quite straightforward. And the other part of enrichment and applying rules, that's a separate thing. So David and I, we just split the problem. David stayed with the predict step, and I stayed with the rules to find a solution how we could cut the cost of things. And proportionally, so we can understand within the pipeline how much processing time was spent with each step. We were, by the time, using this pipeline for several rails in the BBC Sounds app, some of them with more, some with less rules. But the prediction step costed more or less 40% in every pipeline, whereas the rules application was 60%, even in pipelines who almost didn't have any rules. So it was much in the enrichment phase, and in the other steps, we were just passing too much data, and we didn't need that. So the work David did, some of the lessons there are quite similar to what Mark mentioned. So he played a lot with batching. He played a lot with changing threads, numbers. This was the best setup he managed to have. Hopefully someday he can come here and describe more about it. And what he did was to get this article and replace it to use LightFM, tweaking the parameters. And then if each of these boxes could be expanded in more steps, and that helped significantly reducing the cost. So depending on the amount of episodes we were predicting, evaluating the score per user, the costs were significantly reduced, for some cases more than others. And then I had the rules side. And for the rules, my strategy was, you know what, this thing of enriching with the metadata, all the PIDs and things, that's a bit too much. It's not working. So I tried to think for each of the business rules, what would be similar to what Mark described of trying to pre-process what you can. So I tried to think, okay, narrative arc, what would be the minimum data structure which could be shared as a side input or something, where I could just say, given this branch, given this drama thing, this is the order. If the user is here, next episode is this. So I tried to have the minimal information as tiny side inputs for each of the business rules, and to really just pass to each step the minimum we needed. So the IGs and things. And this worked. So this is the squeezed representation of the pipeline. Here is with all the steps of filtering and doing things. And the cost reduction was, let's say if the rules were costing £150, they costed £2 or from 100. So we were able to really reduce a lot the cost. So it is still not perfect, right? So, but we still were able to reduce to 80% of the original cost and 82%. And there are other problems to solve. Some of the takeaways we had, similar to what Mark said, it is important to use meaningful and representative data since the beginning. Sometimes the pipeline might not be in the best shape, but it might still solve a business issue. The costly pipeline was still cheaper than the third-party provider the BBC was hiring. Reducing the scope was a good way for us to get something out there. Simple problems, which are just programming problems, right? So apply rules, process what you can before having to do for the millions of users. Reducing the sorting issue, which we knew was expensive. At the moment, we're using, similar to what Mark said, Beam operators to do sorting. Machine types can be good, except you wouldn't be able to benefit from FlexRS, for instance. So that's a lesson we learned. But with the last, when we split the pipelines, we are now using normal data flow instances, the standard one, so we're able to benefit from this. Just adopting shared memory, if you don't tweak other things, might not give the gains straight away. Our lesson was that we should keep the interfaces as minimal as possible, but this is probably not only our problem, data engineering as a whole. And splitting the pipeline helped significantly reducing. So yes, that's it. Yes, thank you. Does anyone have any questions? No, everyone wants pizza. Some questions.
No, if I understand correctly, the model is being uploaded on the worker and the inference happens there. Have you considered making that part external and putting the model, I think Vertex AI is the canonical one these days in Google Cloud, and then calling it over HTTP endpoint, maybe do batch inference or something like that?
Yes, yeah. So we did consider, we probably opposed choosing Vertex AI. What we were considering was to load the model in a custom container image, opposed to retrieving it during the setup of the DoFN. And that's something we're willing to try, but we didn't yet. I would expect that perhaps loading from Vertex might end up being more expensive, and it would also make us dependent on a proprietary technology, but those are things we can certainly consider.
In terms of cost optimization, you mentioned about the more expensive code. You compare that with other technologies or the cloud vendors in terms of seeing alternatives, or?
Yes, so one of our ideas was, of course, get rid of this type of model and calculate the scores in a different way. And one of the strategies we found for this was to have approximate near neighbors. And we were able to replace this sort of implementation of predicting for the users using the model itself by exporting the sparse matrices and computing the nearest, the highest ranking approximately. And this allowed us to reduce much, much more. So I think it allowed us to reduce, let's say, from 50 to 3 pounds or something. And then there would be other ideas of using other technologies and things, but so far we haven't explored those paths.
I mean, it's just a comparison, right? Because obviously it was expensive, but trying something else, oh, you will compare with that, right?
Yes.
Optimizing, trying to
Yes, we tried, and yes, and then the idea now, I think the plan is to just leave this platform and then attempting other technologies as a whole, other approaches, other models, other strategies. This was the starting point. Yes.
Congratulations for the improvement. It's very, very great.
Thank
I'd like
you.
to know how are you using Airflow in the middle of this pipeline? Or why are you using Airflow in the middle of the...
Okay, so Airflow, yes. So Airflow, it's not used for the pipelines themselves, but let me show you something. So this is our production environment. Dun, 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 dun. Let's see. Yes, I'm on call today, so if anything goes wrong. So the way we use, at the moment, Cloud Composer, shame on us, we're using a very old version. But we have a few DAGs where we trigger things. So we have Kafka, and then we ingest things from Kafka, and then we call some of the Beam pipelines to train the model itself. For instance, we use GK operators. So we train the model because it just scales vertically. So as an example, this is an example, and we parallelize for many use cases we have and things, and we call different operators. Oh, look, we're training a model right now. And then some of those boxes are Beam, some are not. Some are just Python operators. And we really tried, when we had a problem, we can just split this into multiple workers and delegate it. That's when we used Beam. But from a more overall perspective, we need to have retries, or we want to, since we're not using streaming, and we were not using PubSub or anything, Airflow is our glue there. So we trigger all those pipelines and things from there. Yes. Any more questions? Pizza time then. Thank you.